Hello, Heron students and Riverside students. Today we're going to be talking about Skill 16, which is graphs of logarithmic functions. So if you remember, we had previously talked about exponentials and logarithms and how they're related. So we're going to go into a little bit more in-depth about how that is represented graphically and see if we can define these relationships a little bit more clearly. To start off, I'm going to review our exponential function is something like a to the x, x being our exponent and our variable. So I'm going to use an example, 2 to the x, and I'm just going to graph that equation really quick. I'm going to choose 2, -1, 0, 1, and 2. And I'm going to solve my exponential function for those x values. So 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0, anything to the 0 is 1. 2 to the first power is 2, and then 2 squared is 4. And I'm going to go ahead and graph that. There's a 2 to the -4th, or no, I'm sorry, -2, 1/4, -1, 1/2, 0, 1, and then let's say 1, 2, and 2, 4. So right there. And then I'm just going to come across this x-axis here, follow the curve of my points, and shoot off into the sky. That is not a fantastic start, but we'll get better at it. And now I'm going to think about how that logarithmic function, log2 of x, is going to look. Now if you remember, the logarithm function is an inverse function of an exponential function. And what that means is our x's and y's are actually going to swap places. We talked about this last lesson. So I am just going to copy down my x values as y values and my y values as x values. And then I'm going to graph that. There we go. So all I've done is taken all of these x values and made them y's right here, and all of my y values and made them x's. These are swapped. And I'm going to graph that just as it is. So I'm going to go to 1/4 -2. That's right about here. And, oh, that's about 1/2 actually. And then we'll do 1/2 -1. We'll put that right there. 1, 0 is right here. 2, 1 is right here. And 4, 2 is right there. So I'm going to come across my y-axis on this one, following the curve of this line, like that. That was much better. Okay, so we can make a table for a logarithmic function just by inverting the exponential function. So if we have an exponential function that we can use, we flip it, the x's and y's become our logarithmic coordinates. A couple of questions that I want to go through. These are on your notes as well. What do you notice about the table of values? We notice that the x's and y values have swapped. What that literally means is that our inputs, x's are our inputs, right? X's are our inputs, became our outputs. Okay? Which means that our y's are now our inputs. I want to keep that in mind as we go through these. Okay? How do we describe the relationship between these two? Well, we talked about that in Skill 15 as well. They are inverse functions. They are inverses. And I know this is sounding a lot like just review, but that's because I want to make sure that you guys understand how these two functions are related. Can we make a line? So this question is, can we make a line so that it is, when it's reflected, the exponential function becomes the log function, right? Now, to do that, we need to think about what a reflection is, right? We're flipping it over a line. And the line is actually going to be right here. Right here. And the equation of that line, yes, the equation of that line is going to be y equals x. We flip this over the y equals x line, and it becomes our log function. Our final question is, suppose we put in 0 for g of x. What sort of answer would we get, and why? Well, if we look at our log function right here, 0 for x is this line right here, right here. What kind of values would we see if we plug this in, right? What would our y value be? Well, we already know that's going to be something not positive, right? Because from here on, we're no longer positive. The fact of the matter is, just like our asymptotes were horizontal in our exponential functions, our log functions are going to have vertical asymptotes. So this is our vertical asymptote, so we're not going to get an answer here. We're going to get an error. And that is because it never reaches 0. And this is a key concept that we're going to talk about, all right? Remember we talked about how our logarithmic function always has to be greater than something, right? Our vertical asymptote. So let's compare them graphically. We've got them done. What kind of concepts can we draw here? We're going to do the same thing that we did when we first learned about the factors and the traits of our exponential function, right? The intercept of 2 to the x is 0, 1. That is a y-intercept of 0, 1. For the logarithmic function, we're going to start looking at x-intercepts, and our x-intercept is 1, 0. And that makes sense because our x's and y's have swapped. The domain of our function, all of our x values, right? This exponential function is going to continue from left to right forever. So our domain, as we remember from our test, is negative infinity to positive infinity. However, our logarithmic function does not go everywhere from left to right. It hits that asymptote at x equals 0 and stops. So our domain stops at 0 and goes to infinity. However, our ranges are we're going to see a pattern here. The range of our exponential function, we have our horizontal asymptote right here at x or y equals 0. I'm sorry, y equals 0 here, and then everything above that has a y value and an x value. So our range for an exponential function is 0 to infinity. And if these two things swapped, it's reasonable to assume that these two are going to swap too. And we can see that that's true. This function goes forever down and will continue to grow, however slowly, forever. So it is going to have a range of negative infinity and positive infinity all the time. So these two things have swapped. Our asymptotes, as we've already talked about, our asymptote for our exponential function is y equals 0, and that is a horizontal asymptote. We draw a horizontal line. And we've talked about kind of how this function stops at when x is 0, which is a vertical asymptote. So how do they relate to each other in the asymptote? All of the functions swapped. Everything swaps. Everything switches. Oh god, I can't spell switched. Domain becomes range. Becomes range on a log function. And our asymptote becomes vertical. Okay? So now we're going to look at a couple of other things. We're going to fill out this table for the log of 2 of x, right? Remember that when I talk about the log of x, the question that's being asked is, what power do I have to raise to 2 to get x, okay? So when I fill these functions in, I'm going to have g of x equals the log of 2 of x, and I'm going to replace all of my x's. G of 8 is going to be the log of 2 of 8. Okay? The question is, what do I have to raise 2 to get 8? Okay? A little bit of simple math, we can see that the answer is 3. I raised 2 to the 3rd power to get 8. So my g of x is going to be 3. Follow the same pattern. G of 4 is going to equal the log of 2 of 4. Okay? Question is, 2 to what power gives me 4? 2 squared. And the last three are a little bit unique, right? Anything, the log of 2 of 1, right? 2 to what power gives me 1? That's always 0. Anything to the 0 power. But when we get to 0, we have a problem. What do I raise 2 to get 0 as an answer? Well, there's nothing I can raise that to, so I'm going to write error, or incorrect, or impossible, or NA, a lot of different answers, right? I can never have a power that will make me result in a 0. If I use a negative number, I get a fraction. If I use 0, I get 1, and anything in between is just going to give me a whole number. Likewise, if I have log of 2 of 6, negative 6, sorry, there is no power that will give me a negative answer. No power that I can raise 22 will give me -6. So that is also an error. And what this tells us about our argument is this thing right here. It is x. It's everything in that parentheses. It tells us that our argument has to be greater than 0. Greater than 0. Okay, so x has to be more than 0. Now let's look at what these functions do once we started to do stuff. And oh my goodness, Microsoft Excel has decided to jumble all this up. We can fix that though. We have the log of 2 of x. This is what the log of 2 of x looks like. Okay? When I flip it down, I am going to have the log of -x. If I want to flip it so that it is shaped like this, I'm going to have the negative log 2 of x. And then this last one is going to be a combination of both. It's going to be y equals the negative log of 2 of -x. Okay? One thing I want to note here, just because this says -x does not mean that our argument is negative, right? We can't have a negative argument. So when I say -x as an argument, that means that the only numbers that work are negative numbers, right? If I pick -3 to plug in here, that is going to result in a -3, which is equal to 3. Okay? And that makes sense because all of these numbers here that fit on our -x log are negative numbers. -5, -4, -3, -2, -1. So I'm going to let you guys go ahead and try this on your own. I'm not going to go through it just to save time. And we'll move on to our tables here. So I have 4 different log functions here, and we're going to see how they compare. We've already done one. We know the answer for our x-intercept is right here. Our domain is going to be from 0 to infinity. This is just a regular log function of 2x. And our range is -infinity to +infinity. And our asymptote is at x equals 0. Okay? Now, when I change it, when I subtract 2 here, that's this function, we are going to get a couple of different answers. We know that just looking at this, our x-intercept is 3, 0. Our domain is now, our asymptote is looking like it's going to be at 2, so I can fill that in. My domain is going to be 2 to infinity. My range is going to be -infinity to +infinity again. So we've seen that this has moved over a little bit. It went up 2 on compared to our regular x-intercept, right? This is our normal x-intercept right here. Now let's do log 2 of x minus 2 right here. I'm going to do this one as a sum, just so that they're a little bit different. We can see that our intercept here is 4, 0. Our domain, it actually goes back to our original one, so it's going to be 0, infinity. And let's see, we are going to look for, oh, I'm sorry, our range is always going to be -infinity to +infinity, and our asymptote is at 0. Okay, so we've seen some changes, we've seen some things stay the same. The final one I want to look at is the log of 1/2 x. We're going to call that the smelly face right here. This log has the same x-intercept, same domain, same range, and same asymptote as our original log function. The only thing we can tell visually is that it sort of slowly grows. It goes a little bit slower. So the number in front is going to affect the slope of the line, not any of those key features that we're looking for. So, things to generalize, right? Our base x-intercept is 1 to 0. And then our number inside here, our number inside designates a shift. It's going to move our x. Moves our x. Let's write a k. I'm going to use that as it. Actually, I'm going to